This problem's asking us to determine the intervals, so x intervals, where the given function is concave up and concave down. So anytime I see the language concave up, concave down, anytime somebody wants me to find those intervals, bells and whistles got to be going off that that is a second derivative test. And so that's exactly what you're going to do here. We're going to run a second derivative test. The second derivative test is identical to the first derivative test. You do the same exact processes, except on the second derivative test, guess what? You use the second derivative for everything. And because it's a second derivative, it tells us different information. But process-wise, it looks the same. So step one of the process, guess what? You want to find your second derivative. So we take our equation, f of x equals 3x to the fifth minus 20x cubed, and we find the second derivative. So doing the derivative once, applying our power rule, we just have a bunch of stuff being added and subtracted. We bring the 5 down, 5 times 3 gets us 15x, subtracting 1 from the power gets us x to the fourth. Bring that 3 down, 3 times negative 20 gets us negative 60, subtracting 1 from the power leaves us with x squared. So first derivative done, on to finding our second derivative. So the second derivative, guess what? We're just going to take the derivative again using the power rule. So this time bring the 4 down. 4 times 15 gets us 60x. Subtracting 1 from the power gets us x to the third. And then we're going to bring our 2 down. 2 times negative 60 gets us negative 120. And then x subtracting 1 from the power leaves us with x to the first. So step 1 complete. Now on to step 2. Instead of finding critical values, we need to find our possible inflection points. Well, guess what? Critical values happen when the first derivative equals 0, so possible inflection points are going to happen when the second derivative equals 0, or just like with the first derivative, when the second derivative is undefined, not f double prime. So this would be f double prime of x equals 0, and f double prime of x, our second derivative, is undefined. So undefined, like we've talked about, if you've got fractions, whenever you would have division by 0 in your derivative, that would be a place where it is undefined. And also if you've got an interval given to you, then those endpoints on that interval are going to be what you're looking at. So here we don't have any division by 0 to worry about because we don't have any fractions and we don't have any closed interval, so we don't have to worry about the endpoints. That means all we need to concern ourselves with is the standard, setting this thing equal to 0. So we take our second derivative, set it equal to 0, and then solve for x. When you look to this problem and think about the algebra moves you want to do here, remember that anytime you got a power of 2 or greater on your equation, odds are you're going to need to factor that thing in order to solve it. And so for sure we're going to want to factor this equation as well. So I look and first and foremost see what number I can pull out of both. So I can pull a 60 out of both of these pieces, and then I can pull an x out of both of them. So that'll leave me pulled the 60 out of the front, pulled 1x out of that, so that's going to leave me x squared, pulled 60 out of 120, that's going to leave me with a negative 2, and then we took that x out. The reason we do that is now we can go ahead and set each of these problems individually equal to 0 and solve those little math problems. So we want to know when does 60x equals 0, and then we're also going to want to know when does x squared minus 2 equals 0. So solving those little math problems out, on this first one here, I just need to divide by 60, and I end up with x equals 0. That is a possible inflection point. It's important to remember that. Not for sure an inflection point yet. Now we go ahead and do the same thing on the other side. Go ahead and solve this other equation to get x by itself. So we'll add 2, we get x squared equals 2, and then we're going to square root both sides of this. So we're going to get x equals, and because we applied the square root, we get plus or minus the square root of 2. So really out of here, we get 2 different possible inflection points. The negative square root of 2, and then we also get x equals the positive square root of 2. So step 2 complete, and now we're going to go on to step 3, which is again going to be very similar to our first derivative test. So step 3 here, we are going to do the second derivative test. This again is a number line game, just like we saw on that first derivative test. So you're going to start off, draw out your number line, and then we're going to mark all of our critical values. So we have or not critical values, excuse me, we're going to mark all of our possible inflection points. So we've got negative square root of 2. That's a possible inflection point. We have 0 would come next. That's a possible inflection point. And then we've got the square root of 2. That would come next. That's our last possible inflection point. Then, like we saw on the first derivative test, we need to now choose test values from each of these regions here. So I'm going to choose something to the left of the negative square root of 2. That would be negative 3. I'm going to choose something in between negative square root of 2. If you don't know what the square root of 2 is, always put that stuff into your calculator. Turn it into a decimal to figure out what that is so you can pick the right numbers. This would be negative 1. We'll go in between there. I'm going to go ahead and pick positive 1 in between these two. And then outside here, I'm going to pick positive 3 for my test values. This is a second derivative test. So we are going to test all of those values in the second derivative. So we're going to do f double prime of negative 3. We're going to do f double prime of negative 1. We are going to do f double prime of 1. And then we're going to do f double prime of 3. What we get out of here, positive or negative, when we're talking second derivative, it tells us the concavity of the graph. So if we get a positive value out, that's telling us that the graph in that region is concave up like a cup. If we end up getting a negative value out, then that tells us that that region is concave down like a frown. So we just really care about positives and negatives. So I start off, I plug in negative 3, and I get out negative 1,260. So we are plugging this into the second derivative here. Remember, this is a second derivative test. So pop it into your calculator, do what you need to do, but we get out negative 1,260. Only care that it's negative, and that negative tells me that this is concave down. So I put a negative there, and I also draw myself that shape. It just reminds me what's going on. Then I plug in negative 1. Negative 1 is going to give me out a positive 60. So that is positive in this region right here, and therefore concave up like a cup. And again, I just draw it in so that I can read that answer off later. Plugging in 1 to our second derivative, we end up getting out negative 60. So this is negative in this space, and that tells us concave down. And then plug in 3, and we get out a positive 1,260. So again, this section is now positive, and therefore concave up like a cup. So from that, just like when we did a first derivative test, from that information, we're now able to kind of go ahead and draw our conclusions, get our final answer out, answer all the questions that they have for us. The first question they wanted to know is intervals where this thing is concave up versus concave down. So we come through and we just read the data off of our number line from up here. So this graph is going to be concave up wherever we said it had a positive second derivative. So that's going to be in this section here, starting at the negative square root of 2 and ending at 0. And neither one of those is included. Do not include those endpoints in your intervals. So those are parentheses, not brackets. Then you put a union symbol to connect it. And it'll start here at this positive square root of 2 and head off to infinity. So we're starting at the square root of 2, not including it, so parenthesis, and then off to infinity. Infinities are always a parenthesis. So there's our concave up. And then we come through and want to know about a concave down section. So again, reading off of our chart up here, we can see that starting at negative infinity and ending at that negative square root of 2, that's our first section where this thing is concave down. Then we'll union that again, and now it's negative here between 0 and the square root of 2. So that is our other, and neither one of those endpoints are included in the intervals. So again, parentheses and not brackets. The last question on here wants to know about the location of any inflection points. When we are talking about inflection points can happen where the second derivative equals 0 or the second derivative is undefined, but they must also, it must change concavity at that position. So the graph needs to change from going concave down into concave up, or it needs to change from concave up into concave down. Wherever those things happen, that's when we know we've got an inflection point. And so looking at our chart, looking at our first possible inflection point, that negative square root of 2, I can see to the left of that it is concave down. To the right of it, it is concave up. So that is definitely going to be an inflection point at negative square root of 2. So we've got x equals negative root 2. It definitely changes concavity there. Looking at our middle one, this one changes. On the left, it is concave up like a cup, and to the right of it, it is concave down like a frown. So that is also going to work for an inflection point. It changed concavity. And then looking at our last possible inflection point, to the left of that, it is negative, it's concave down. To the right of that, it is positive and concave up. So it did change concavity there. So all of our inflection point possibilities turned out to actually be inflection points. If your interval goes positive to positive or negative to negative, if they're back to back the same sign, that is not an inflection point. So you would throw it out and you would not use it. Now, those are where they happen. We don't know what the actual point is. And so oftentimes they want you to go ahead and get the full x and y values. So we know the x values. To get the y values, we just plug those back into the original equation. Remember that we're really caring about this original equation. So all of the points we talk about need to be on that graph. So we would do f of the negative root 2. Plug that in, we would do f of 0, plug that in, and you would do f of root 2, plug that in. Plugging those back into the original equation. And again, just pop that into your calculator, do whatever you got to do. This first one would have given us the y value of 28 root 2. Plugging in 0, that would have been easy math. That just equals 0. And then plugging in root 2, we would have ended up with negative 28 root 2. So you now have the full points, the x and the y value for all of your inflection points. Thanks for watching my video. If you liked it, please click that like button and subscribe. And also share it with your friends and anyone else you know who might be crying about an upcoming AP Calc test. You can find more videos from me, more sample AP Calc questions, and my complete AP Calc study guide over at my website, apcalcprep.com. Have a great one.